You are observing the traces left in the sky by dying stars, the signature of their last breath. Torrential outbursts of gas and dust that, in the wake of violent stellar deaths, have given birth to planetary nebulae. These thermal pulses currently sweeping through space, although all of them are larger than our solar system and many of them look like open eyes, are invisible to the naked eye. And to be able to see them, we need to use powerful telescopes. Strangely, today, these veils of gas drifting in the interstellar medium are given a name that isn't the right one. Because the term planetary nebula is definitely a poor choice, inherited from a time when it was impossible for us to measure the vastness of these formations. When, at the end of the 18th century, these structures were observed for the first time in the deep sky, they appeared in the rather weak telescopes of that era, like disks that were often nebulous, poorly defined, and slightly green or bluish, similar to the giant gas planets Uranus and Neptune. But even though the use of this name, planetary nebula, has persisted, in reality, they have absolutely nothing to do with the history of planets. Infinitely heavier, brighter, and more short-lived, their presence tells us of a terrible climax. Because these streams of stellar matter, which we might be tempted to imagine as being produced by birth, are actually their final works, their ultimate signatures, those of death by stripping away. When stars with 0.8 to 8 times the mass of our Sun reach the last thousands of years of their lives, they enter a kind of swan song and agony, transforming into red giants. They become hypertrophied versions of themselves, and disturbed by the energy released by the fusions taking place in their outer layers, they begin to swell, to expand their envelope of light, to the point of reaching a prodigiously enormous waistline, becoming up to several thousand times wider than our Sun is today, and even going so far as to eventually send almost all of its outer layers into space. After that, the dying star will slowly and intermittently shape its nebula. By compressing, with the power of its last solar winds and its radiation, the gigantic clouds produced by the expanding outer envelope, whose ionized matter spreads at several tens of kilometers per second into the interstellar medium around a small dying star. At the center of the peeled nebula, all that remains is a bare solar core, a white dwarf produced by the now dead star, which, in its death, gave birth to it. These are the stars, extremely hot and able to contain in a volume about the size of our planet a mass close to that of our Sun, which, through their powerful ionizing radiation, allow us to clearly see these streams of expanding matter. By using high-energy photons to raise the temperature to around 10,000 degrees, these small stars make the surrounding gas shells incandescent, as shown by this nebula, whose blue-green ring is produced by a stellar core that, from the center, emits a stream of ultraviolet light that crashes into the surrounding gas. Here, we can clearly see the residual glow produced by the excitation of atoms making up the sheets of gas expelled by a star in its final phase. There, this other nebula, which I personally decided to name the Eye of Sauron, is illuminated by a bare stellar core, shining with the power of about 9,000 suns combined. Located just 450 light-years away from us, the very photogenic Helix nebula, whose expanding cosmic eye material is illuminated from within, gives back part of the energy it receives in the form of shimmering radiation. It's one of the closest nebulae to us, and also one of the largest ever discovered. If it were visible to the naked eye, the helix would take up half the diameter of the full moon in the sky. It should be said that these veils of gas stretch over distances similar to those that separate us from the closest star to us. These details reflect the image's immensity. Here, every filament of gas is frayed, as we can see on the edges, every drop that shows us. By pointing like so many fingers in the direction of their creator, the precise position of the small and still powerful star that gave birth to them. It stretches from its rounded top to its tail over about 160 billion kilometers, which is roughly 1,000 times the distance between the Earth and the Sun. And all of this fits inside each of these tiny droplets. It is believed that these huge comet-shaped droplets, which are found on the edges of many nebulae, owe their entire existence to the encounter between hot, diffuse stellar winds and drifting matter, denser and colder, ejected by the star here some 10,000 years ago. From this encounter, between the recent fire and the flow spat out by the star in the past, these strange droplets form in the direction opposite to the current. And then, already incredibly large, most of these nebulae are actually much vaster and more complex than they appear. And now, the appearance of this cauldron of incandescent gas changes completely when observed in wavelengths other than visible light. Observed in the infrared spectrum, the Helix Nebula reveals other aspects of its reality to us. Then, at the center, heated by the burning core, a disk of dust appears, along with the very last layers of gas recently expelled by the dying star. And here, made visible through the reflections of a powerful red glow surrounding the small white dwarf. Here, this other nebula, called the Ring Nebula, which visually resembles the Helix Nebula with its cometary knots, each several billion kilometers long, turns out to be much larger than it appears to us when observed in composite light. And you can see that the layers of peripheral matter ejected by the star, which created this cocoon expanding over more than a light year, actually extend even further beyond. Here, each dark-colored petal spread against the starry flag of the deep sky. They were all formed by the star's initial eruptive phases. And over time, as they diluted, they cooled down to the point of eventually leaving the visible domain. Here, as in many other nebulae, it's the behavior of the tiny, barely perceptible white dwarf at the center that, in a second phase, sculpted and shaped it from the inside, with powerful bursts of thermal pulses. The drifting sheets of matter ejected by the late red giant. In this other picture, you can see a nebula formed by this dying little star, with an already impressive size of half a light year across. When observed in the visible spectrum, it is actually still underestimated, as shown in this picture taken in the near infrared. Depending on their life history and the characteristics of the stars that gave birth to them, these nebulae can take on extremely varied shapes. There, spiral cosmic clouds, here, overlapping or interlocking shells of gas. Some have central symmetries, are bipolar or ellipsoidal, while others can be perfectly spherical or even completely asymmetrical, and this at several scales. In short, it's a glorious mess. Here, the two cone-shaped filamentous columns of the relatively young nebula, known as the Ant Nebula, just like the Hourglass Nebula, most likely owe their characteristic bipolar shape to the presence of a thick dust belt that surrounds the star at the center, restricting the flow of stellar winds. Just like the Southern Crab Nebula, where it is suspected that behind the large amount of material encircling the system, there is a pair of swirling, interacting stars hidden. In this other nebula, the spectacular arrangements of drifting sheets of gas and dust are most likely painted by the final dance of a pair of stars, one of whose members is dying out of sight. If the two stars are impossible to distinguish from each other here, it is, as is often the case, because of their close proximity and their orbit being too tight. There, this intimidating nebula in an inverted S shape most likely draws its strangely symmetrical and chaotic structure from the presence at its center of a pair of stars, also engaged in a dance for two. One, dying, has produced drifting layers of gas from its agony, while the other, still very much alive, has disturbed the orientation and arrangement of its intertwined luminous ribbons with its presence. And once again, here, even the smallest details in this image can, in size, defy comprehension. Each of these droplets pointing toward the now vanished giant star is similar in size to our entire inner solar system. In order to feel, almost intuitively, the sheer power released by a giant star that, at the end of its life, ends up tearing itself apart from within. You can gaze upon the impressive wings of the Butterfly Nebula, each stretching over more than 2 light years, shaped by bursts of thermal pulses and ejections of superheated material caused by the convulsions of a star that was originally about 5 times heavier than our Sun. All that remains of this space monster today, at its center, is a dying star that is, for the moment, supercharged. And with its surface temperature estimated at around 250,000 degrees, it literally shines brilliantly in the ultraviolet range. to the point of being able to almost pierce, with the sheer power of its radiation, the thick cloud of dark dust shaped like a torus behind which it is hidden. In this nebula, as in many others, defying any sense of order, the gas and dust have been ejected in sometimes chaotic rhythms and irregular directions. In great surges, spilling out into space at about 400 kilometers per second, that's a speed that would allow you to travel from Earth to the Moon in less than 20 minutes. One of the most striking and perhaps complex nebulae known to date is the one called the Cat's Eye. Here, the outer shells of gas were ejected at regular intervals before the rhythm and orientation of these pulses changed over time, to the point of drawing around the dying star a structure of nested onion skin layers, a series of overlapping pupils and irises formed by about 10 concentric dust rings, each containing as much mass as all the planets in our solar system combined. Although studying these rings now allows us to shed light on part of the history of this nebula, it is still difficult to decide with certainty between the different scenarios that could explain its fascinating shape. Were the pieces of this cosmic puzzle shaped solely by the variations in the magnetic activity of the dying star, whose light would have later and gently sculpted the ejected materials? Or did the rings of gas shooting out at high speed collide during their history, creating massive cosmic shockwaves? Unless, here too, a binary system is hidden at the center of the eye, disturbing the orientation of the solar winds and creating these concentric dust patterns that you now observe in a composite of optical light and X-rays. In any case, here too, when zooming out significantly, you can observe a vast, diffuse, and extended halo of matter surrounding the small nebula. It is believed that this vast fading structure was ejected during earlier eruptive phases, when the star at the center was still a red giant, some 50,000 to 90,000 years ago. And the craziest thing about all this is that by carefully studying the images coming from these last breaths of stars, astronomers can even deduce their composition, the list of their ingredients. Because the light that reaches us from these expanding veils of gas is rich with valuable information. It contains, encrypted in its electromagnetic spectrum, the proportion of each atomic element, the chemical compositions. And it is based on the intensity of the received radiation, as well as the composition of elements, that astronomers assign colors to these nebulae. I refer you to the episode that explains how light is an incredible key to studying the universe. Here, the Egg Nebula, which appears surrounded by cosmic waves undulating around a star hidden beneath a thick veil of dust. It also has a powerful beam of light that, emitted from the center, reflects off particles the size of those in our fireplace smoke encountered along its path. A large part of this fine interstellar dust is not made up of hydrogen, the basic element of stars, but of clumped carbon atoms that were created and then expelled into the surrounding space by the dying star. Now, on Earth, carbon is the backbone around which life is built. Thus, from the gas shells of the Egg Nebula, as well as from all the dying stars we have just flown over, great promises can be born. And even if one is tempted, setting aside the sheer beauty of the spectacle, to see these events as grim funerals, or rather, formally, in vast cosmic shrouds, stars and planets that, before the advent of this cataclysm, may have orbited around them. These nebulae, counterintuitively, by reminding us through their presence that stars are not eternal, are ultimately very good news for the cosmos. Because the death of these stars means the birth of many other things. In a previous episode, we saw that stars don't just emit light, they are also, and above all, gigantic factories that transform matter. At their core, their temperatures are such that they are able to fuse light elements to transform them into heavier elements. Thus, these nebulae, by expelling into the interstellar medium a large part of these new elements forged on the outer layers of red giants, play a crucial role in increasing the complexity of the elements present in the universe. By enriching the interstellar medium with their presence, they will help seed the cosmos and thus form second or even third generation stars. Stars around which planets enriched with more complex elements may revolve. Here, these deaths leave no room for sadness, because all these new elements hold the promise of a coming great wealth, of an environment enriched with new elements. which may one day end up forming those gigantic clouds from which stars are born. And then, observing these brief final stages in the lives of many stars also teaches us about our own destiny. Because in about 5 billion years, when the hydrogen in the core of the Sun runs out, and when the core of the star, unable to counterbalance the gravitational force that tends to make it collapse in on itself, sees its temperature rise until it reaches 100 million degrees. Our star will then, in just a few million years, head toward these visual apotheoses. The ultimate sunset, which inevitably awaits all stars from 0.8 to 8 solar masses, after which what happens? Even the small central dwarf will eventually end over timescales of several tens of thousands of years, seeing its temperature become too low to illuminate its nebula from within, which will then stop shining. Having become difficult to access, the spectacle of its dissolution will nevertheless continue, taking place far from prying eyes. As shown to us by the old Medusa Nebula, which is already 4 light-years across. And because of the declining activity of its core, which is about to stop, it is preparing to disappear against the black velvet background of the distant universe. In these other images taken 20 years apart, you can see the Stingray Nebula changing shape, and while it continues to expand, it loses a significant amount of brightness over time. Here, the gas clouds of the Boomerang Nebula, which you are currently seeing in a whole range of different wavelengths, have been, in a completely counterintuitive way, measured at a temperature barely 1 degree above absolute zero, which makes this region one of the coldest places in the known universe. This apparent strangeness is explained by the expansion over time of the gas originally expelled from the star at nearly 500,000 km/h. Although planetary nebulae have been studied for almost a century, they still have many secrets left to reveal. Thus, we still do not know where the enigmatic and unusual Red Rectangle Nebula gets its astonishing staircase-shaped structure from. Does this come from its relative youth and the fact that the powerful light of the star has not yet had time to illuminate and ionize all the layers of gas that it has shed itself? These are questions that remain unanswered, and it is strange to think that these phenomena, although extremely common in the cosmos, are known in only small numbers. Among the roughly 200 to 400 billion stars in our galaxy, we have so far detected only about 1,500 of these structures. It must be said that the apparent lifespan of these final fireworks is, compared to that of the stars that create them, completely insignificant. Relatively speaking, compared to the lifespan of their stars, these fade away as quickly as the colors of a sunset fade for us.